You know, when you click Buy Now, you're kicking off this incredible hidden ballet of robots. Deep inside these massive warehouses, hundreds of machines are just zipping around, grabbing your stuff, and getting it all ready to ship. But behind that smooth one-click service is a massive and potentially very expensive traffic jam just waiting to happen. So how do you stop this high-tech dance from turning into a billion-dollar pileup? Let's dive in. We're talking about a world of logistics that completely runs on robots. From giants like Amazon to fully automated shipping ports, these fleets of machines are really the backbone of how we get, well, everything. But think about it, how on earth do you tell hundreds of robots where to go, all at the same time, without it just turning into total chaos? Okay, so this image here, it just perfectly shows you what we're up against. What you're looking at are automated guided vehicles, or AGVs for short. Each one has a whole list of jobs to do, and you can see their little routes mapped out. The real challenge isn't just getting one robot from point A to point B. It's choreographing the entire fleet so that the whole operation is as fast and efficient as it can possibly be. And the scale we're talking about is just mind-boggling. Some warehouses have more than 100 of these AGVs running around at once. And this isn't brand new tech either. Automated ports have been using them since the 90s. But back then, things were a bit more manageable. Today, as the number of robots and tasks just explodes, the problem of directing them all gets exponentially harder. So this isn't just some logistical headache, it's actually a fundamental and really tough challenge in mathematics and computer science, one that deals with a truly dizzying number of possibilities. This kind of problem actually has a name. It's called combinatorial optimization. Imagine you have, say, 5 tasks and 3 robots. The number of ways you can assign those tasks is something a computer can handle. But what happens when you have hundreds of tasks and dozens of robots? Well, the number of possible schedules blows up into the trillions, and then beyond. And finding that one single perfect, most efficient solution in all that noise, it is an absolute nightmare for any normal computer. This is such a great way to think about it. You've probably heard of the classic traveling salesman problem, right? Finding the shortest possible route for a salesman to visit a list of cities. Well, this is like that, but on steroids. It's not just one salesman, it's a whole team of them, and they all have to coordinate perfectly to get their jobs done. All right, so if this problem is so incredibly hard, how have we been solving it until now? Well, that's where our story kind of hits a brick wall. For years, the go-to method has been something called mixed integer programming, or just MIP. You can basically think of it as a way of writing a super detailed, super complex rulebook for the robots. And, for smaller scale problems, it works great. But, and this is a really big but, as the problem gets bigger and more complex, the time it takes to find that perfect solution starts to become a massive issue. Just look at this graph from the study. It tells the whole story. On the bottom, you've got the number of tasks, and on the side, how long it takes to find the best solution. For the first few tasks, it's almost instant, no problem. But watch what happens. At 10 tasks, it jumps. At 11, it absolutely skyrockets to over 300 seconds. And then, get this, for just 12 tasks, the classical computer couldn't even find a solution within the 30-minute time limit. It just gave up. So that's the breaking point. That's the wall where classical computing just can't keep up anymore. So the researchers decided to bring in a whole new player, one that operates on a completely different set of rules. The big difference really comes down to the most basic building blocks. A normal computer bit is like a light switch. It's either on, which is a 1, or it's off, a 0. Simple. But a quantum bit or a qubit is where things get weird. It can be a 1 or a 0, or it can be both at the exact same time. It's a mind-bending principle called superposition. And because of that, a qubit can explore a vast number of possibilities all at once, giving it a totally unfair advantage for problems like this. Now, the researchers didn't use just any quantum computer. They used a really specific type called a coherent Ising machine, or SIM. Think of it less like a general-purpose computer and more like a highly trained specialist. It actually uses pulses of laser light as its qubits, and it is designed for one job and one job only, to absolutely crush these kinds of optimization problems. And maybe the best part of all, it works at room temperature. A lot of quantum computers need to be kept near absolute zero, which is incredibly difficult and expensive. This machine is way more practical. So, the stage was set for a showdown. You've got the old guard, the traditional computer, versus the new contender, the quantum machine. Same problems, two very different ways of solving them. So here's how they set it up. First, they created a bunch of these AGV scheduling challenges, from pretty simple to really, really hard. Then, they gave those challenges to a standard computer, a regular Intel Core i7 running that traditional software. After that, they took the exact same problems and gave them to the coherent Ising machine. The goal was simple: who finds the best answer faster? And the result? It wasn't even close. The quantum machine, on average, saved 92% of the computation time. Let that sink in. 92%. That is a staggering leap in performance. This table really tells the whole story. For a simple 4-task problem, the quantum computer was already about 8 times faster. But look what happens when the problem gets just a little harder. At 6 tasks, it's over 120 times faster. By 7 tasks, the traditional computer takes 234 milliseconds, while the quantum machine solves it in less than 1 millisecond. The gap just keeps getting wider and wider. So a 92% speedup? That's way more than just a cool number on a chart. This has profound real-world implications for how our world actually works.
So what does this all mean? Well, it means warehouses can run much more smoothly, getting more stuff packed and shipped with the same number of robots. For us, that means faster deliveries. And because the whole system is more efficient, it means less wasted energy, which is a huge deal. But maybe even bigger than that, it gives us a brand new tool to tackle countless other complex problems in other industries. This is a real game changer.
The researchers themselves really put it best. They didn't just find a slightly better way to do things, they proved the superiority and great potential of a completely new kind of computing. This isn't just a small improvement, it's a paradigm shift. And that brings us to the final and honestly, the most exciting point. Solving warehouse robot traffic is just the beginning. This same class of impossible optimization problems exists absolutely everywhere. In drug discovery, in financial modeling, in creating new materials. So the question we're left with is a pretty exciting one. If quantum computers can untangle this knot, what other massive world-changing problems are they about to solve next?